Welcome to EE 555 discussion on Wednesday, February 19th, 2014.
Okay, good morning everybody. Today we'll see three problems on queuing and leaky bucket, and I think they are fairly easy, so you can follow, ask questions, and all right, let's start with the first one. There are two users. One is using Telnet and the other is using FTP. Both send their traffic via router R. The outbound link from R is slow enough such that both flows have packets in their queues at all times. Discuss the performance seen by Telnet and in one of each of these cases. When round robin, when fair queuing is used, and when modified fair queuing is used, where we count only the cost of bytes, not headers. Okay? So we need to compare those three cases, and also Telnet packet consists of 1 byte payload and 40 byte headers for TCP and 24 IP, and the FTP packet is 512 bytes data and same thing, 20 and 20. Okay? So let's see which one is better for all these three scenarios. Any questions? It's simple, right? Okay, so analytical derivation over here, we can just think, how each scenario works and argue that the other or not. So the first case is round robin. What do we do in round robin? We have basically two flows. One is Telnet and one is FTP, right? And we want to serve these two guys. They have packet size, and we do round robin. So what's going to happen? We alternate, right? One time the other. So who is getting better in the sense more bandwidth? FTP. Exactly, that's all we can say. We don't need to do anything more. We can just claim that it gets much better service because it has a bigger packet size. All right? How to phrase this? Round robin service, we will alternate one Telnet packet with FTP packet causing Telnet basically less throughput. Okay. How about the second case where we use fair queuing? Fair queuing, we don't need to do any analysis. We don't have any procedure for how. We just have packet sizes. Okay, so any ideas? Fair. How many bytes for each per unit time? Or do we allocate more to one flow and less to the? The smaller gets priority? But we have continuous arrival of packets, right? So there is no, we don't know that then it's gone. But you have a point that since the first packets, is it? Yes. Telnet has smaller packets, so in fair queuing, we will serve this guy more often because they want to get the same amount of throughput. It's fair queuing, so we don't really care how the packets are split. We care about providing them the same bit per bit, right? Make sense? So we send roughly equal volumes of there are about packets correspond to its, how many FTP packets correspond to one telnet packet? What do we need to do? We need to sum all the packet, headers and payloads and divide, right? There are about how many? 500, and we have, let me show you, 512 plus 40, 552, and in 91 total. We take into account the headers, right? 552 versus 1, which is equal to 13.5 telnet packets per FTP. That we send 13.5 net packets This is better than number 1, right? Than part A. Any questions? So in the next part, we want to see the modified fair queuing, where in this case we count only the cost of data bytes. We exclude headers. So what happens in this case? Much less payload than its header. We have one. So, and FTP has much higher payload than the header. So we make the difference even more intense now, right? So in this case, what happens? We will send how many telnet packets per FTP? 512, exactly. With we send 5 telnet packets FTP packet. And of course the FTP, right? Okay. So as we see, this small difference in where to put the weight, or if you look at the header or not the header, might change. That was a simple problem, I guess. We don't need to talk more about that if you don't have other questions. Okay? All right. Let's go to the... Okay, problem number 2. Consider the figure. Answer the following questions. So we have the arrival process here. We have the time. We have the packets arriving in each time slot from 0 to whatever. Another time line that represents the departures. Here is when the packet is being transmitted. The transmission is complete, meaning over here. Transmission starts, for example, for the first guy, he's by himself, number 1, he goes to the, and he's being transmitted. All right? Also, in each time, more than 1 arrivals. For example, in time slot 0, we have arrival of packet 1 and 2. That's the story. It's very simple. We have some out of order packet arrival. For example, 1, 2, 3, 4, then we have 6, and then 5. That kind of might, make things more. So we need to answer to the following questions now. Oops. The questions we will do over here, we'll do A and D. And before I forget, do the part B, C at home. Okay? You are not going to be graded for that, obviously, for you. All right, in part 1, part A, assuming FIFO service indicates packet 2 through 12 each leave the queue. For each packet, what is the delay between each arrival of the slot in which it is transmitted? What is the average of this delay over all 12 packets? FIFO discipline, and we need to find essentially the delay. Right? So to find the delay, we need to find the time that each packet starts being serviced, or it will go to the server. Make sense? Okay. So let's see how we can tackle this problem. This graph here, right, on this diagram. So we have FIFO, the order the packet arrive, this is the order they're going to come out. So we expect to have 6 coming out before 5. And so on and so forth. Really sophisticated, I think. Let's too many papers. Okay. There are 2 ways to, solve or analyze this problem. I don't know if you want to do it with, or you can do it with just a table. And with equations, I don't mean something really smart. Just see between the delay or the departure time of one packet and the we need to analyze, basically. Because it's a FIFO, right? So one comes after the other. Size 1 of the packet. The departure time of one guy is what? The time the next packet leaves the queue and goes to service, right? And the same for the delay. Okay, so I think we can proceed as follows over here. This is part A, right? Delay of packet I, where I'm going to write this with I here, the order or the packet in order of arrival, which means 6 is before 5, okay? You can make a function over here or something like that, that maps indexes to arrival time, but let's keep it simple. In order of arrival time, i.e. not in order of packet number. Okay, so the delay in this case is what? The departure time from the queue minus the arrival time. Right? Is the delay waiting in the queue. We subtract the time it departed the queue to start minus the arrival time. So we have departure time from queue of packet I minus arrival. Okay, arrival time. I guess you are all right. And also, if we want to further analyze this, this is also departure minus arrival plus 1, right? Departure time overall minus arrival service time, which is 1. But we don't need that. Okay, what else do we know? We know that also departure time from Q for packet I, how is this related time from the Q for the previous packet? Is the previous delay plus 1, right? Why is that? Because there is a gap in between of the previous packet. Do you agree? Okay. So this is equal to one. Okay. I'm sorry. Plus 1. All right. So now table and find all the times we want. So I'm going to represent first of all the arrival times. So we have here, let's put the packet number, then the time this happens, and the delay. We have a time 0, we have packet 1, time 0. I'm copying this from the graph, okay? I'm not going to read it, I'm just copying this from this graph. This is 1, this is 1, 3, 3, 5, 5, 7, 8. And then what else do we have? We have packet 3, 4. I'm going to put 6 first for the reasons I told you earlier. 7, 5, 8, 9, 10. Okay, so now let's see what is the departure time from the queue for the first packet. It arrives at 0, goes straight to service. Okay, so it departs from the queue at time 0. It's not from the system, it's from the queue. The delay is 0. Minus this. 0. Make sense? Okay. So for the second guy, we know that the departure is the previous plus 1. Without even thinking about it, you can just apply. If you show arrival, where we did over here, you can fill in this cost by applying the equation. But let's think about it. So the second packet went into service at time 0, which means it came out at time 1. At that time, packet has arrived. It's already there from time 0, right? So in at time 1. This equation applies given that the server is always busy over here. Eh? If you have gaps, obviously we need to add the gaps too. Okay. The third guy. The third guy, this guy will come out at time 2. Here, time 2 it comes out, it has arrived already, so it goes to service. So we have 2 over here, and I'm going to fill in the delays at the end. Do you agree? Do you agree with the pattern? Yes. Analyze more, right? So 3, 4, 5, 6, 8, 9, 10. And I'm telling you, this happens because if you see, you need to go one by one and see that the server is always busy. So one new packet when the previous leaves. Okay? And the delay in this case is we subtract these two. 1 minus 0, 1, 2, 2, 2, 3, 2, 2, 2, and 3. And now the question asks, what is it? We just calculate the average. Equals to 1.91 if you do the math. All right? Do you agree, guys, with that? Okay. Now we can continue with the next question, which is, excuse me, it's part D. We assume a weighted fair queuing service. Assume that odd numbered packets and even numbered packets are from class 2. Class 1 has weighted fair queuing weight of 2, has a weighted fair queuing weight of 1. Note that it may not be possible to achieve a weighted fair queuing schedule. So indicate why you have chosen the particular packet to go into service. For each packet, what is the delay between its arrival and its departure time? And what is the average of all 12 packets? Do you understand the problem? Of packets, we just put, in the odd packets, we put a flag that says class 1. If class 2 has less priority than class 1, and we need to find the weighted fair queuing schedule. All right, so in this case now over here, we won't do the graph and all these things that we did for the last week. We will use the weighted fair queuing approximation, the round-robin approximate queue. Okay? There are many ways to think about that. And in the exams, of course, you should ask what kind of assumptions. But in this particular case, the setup such that either you can assume that the packet has a size of 1 bit, or it's given that we need to use weighted fair queuing round-robin approximation of queuing. Okay? So what we mean by that. Otherwise, we need to do the graphs, you need to calculate finishing times. It's just an alternative. It doesn't mean that whenever you see W here. Make sense? Okay. So, here we have mixed classes. We have class 1 and class 2 mixed together. Is it obvious? It is. It's better we separate those two. We create 2 different timelines maybe, one for class 1, another, and we see how the packets go to service. So let me draw this diagram. How are we doing with time? Okay. We will use, first of all, weighted round-robin approximation of WF queuing. I'm gonna do the same table. 1, 1, 2, 3, 3, 5, 7, 8, 8. The second column here we need to put is packet number. Yeah, I'm gonna do something also in the next page. We need class number. We need the weight. This is life easier. If you want, you can have this in your mind and just fill in the table, but I prefer to have it fast, you know. Departure from queue, departure overall, and also delay. That's what we need, okay? I'm gonna come back. Before that, let's also draw a diagram with the arrivals over time. Let's create one line for class 1 and another line for class 2. class 2. And this is time 0. We have 1. Okay, and also let's now put for the arrival of the packets anyway that arrive. In the first time slot, we have an arrival, and this is packet 1 for class 1. Okay, class 2 arrives also there, the first packet of class 2, and it arrives over here. So put them in a circle to, you know, not confuse them with the time slot numbers, the times. All right. Packet number 3, I'm copying the diagram. Packet number 3 arrives here. Packet number 4 arrives here. And packet number 6 arrives. Packet number 2, 3, 4, 5, 6, 7, 8. Packet number 8 arrives 10 and 12. Alright, for class 1, we have an arrival of 2 odd packets, 5 and 7 at time slot 3. 5, 7, they both arrive at time slot 3. At time slot 5, we have an arrival of 9, and 11 or a time anyway, I'm saying slot, it's not a slot really, at time 8. Do you agree with the diagram? Okay, so now we can see exactly if we do weighted round robin means we put more weight, but we put more weight to the class that has more weight. Okay, proportionally. How much weight it has? The weight of class 2. So in class 1, we serve 2 packets. That's what we do. So let's go back to the table now. In this table we said packet number 1, 2, 3, 4, this is 6, 5, 7, 9, 10, 11, and 12. Okay, the only difference is 6 here. This is, if it's odd, it's class 1. If not, it's class 2. So this is 1, this is 1, this is 2, this is 2, this is 1, 1, 2, 1, 2, 1. And the opposite is the weight. So the weight of the first class is 2. This is 1, 2, 1, 1, 2, 2, 1, 2, 1, 2, 1. Why is that? Because it's given that over here, class 2 has a weighted fair queuing weight of 1, and class 1 is 2. Just even, you know, more confusing anyway. All right, so the departure time from queue now, it depends on the schedule. So all the rest we can fill it up after thinking about the algorithm. All right, so going back here in this diagram, sorry, this is it. If we do weighted round robin, what is the schedule? It's gonna be, we start from 1, this guy goes to service right away. Okay, we're gonna allocate to this class 2, which means if at time the first packet comes out, there is a packet waiting from class 1, it's going to go, right? If not, we will go to class 2, if it has packet 2. So that's how we should think. Pair 1, another pair 1. Okay, and find the delays. I don't know what's the best way to, okay. Maybe. First packet goes in at 0, it departs at 1, we know that. 1, we go to the next packet, we said we are at, so I should go not to packet 2, I should go to packet 3. Is the packet 3 there? It is. Packet 3 arrived at 1. So at 1, I'm going to put packet, which means the departure from the queue happens at 1. Do you agree? For packet 3, parts this plus 1 equals to 2. The delay, let's calculate it later. This means I'm done with the first class. I'm going to the second class. I have packet 2 waiting at time since time 0. Packet 2 is going to be served at the previous packet. So packet 2 will depart from queue at 2, system at 3, and then we do the same. At 3, which packet I'm going to class 1. From class 1, what happens at time 3? The next packet arrival is 5. Is it there? 5 and 7 arrived at 3, so I'm good. My queue is full, right? I'm going to packet 5. It starts service at 3 and it exits at... I need to serve 2 packets from class 1. So I'm going to pick also number 7. 4. Okay, I'm done with class 1. Now I need to serve class 2. At time 5 over here, okay? Time 5, I'm going to the next packet of class 2, which is 4. What time did it? 4 arrived at 1. We are good. So it starts service at 5, at 6. Number 4, I'm done with class 2. I'm going back to class. The next packet from class 1 is 9. And my timer, my clock says it's 6. I'm going to packet number 9. It arrived at 5, so we are good. Enter service at 6 and exits at 7. If you do it step by step, it's very easy, right? Okay, so 7 is when packet 9 exits. I am at class 1, I need to, but I don't think I have one. We are at 9, we are at time 7, we are here, meaning have another class 1 packet. What do? We switch to the other class, right? Mark this state as for further comment anyway. We'll add, and okay, 9, then we need to go to 6. From 6, we go, what time? This is 7. We enter service at 7 and exit at 8. I'm done with class 2. Alright, so we go back to class 1. The time is 8. 11 has arrived. So I'm going down to 11. It enters service at, it exits at 9. And then nothing else. Over here, as compared to the previous one, which is that the flow is over. Okay, say the flow is done. So now we don't have this, oh, okay. Packets from flow 1, no, flow is inactive. Okay. So what is the time over here? It's 9, packet 11. Then we go to, we stopped at 8. Packet 8 is here. So we enter at 9, we exit at 10, keep serving these guys. Then we go to packet 10. Packet 10 is here. We go out at 11 and 12 is here. 11 we go out 12. Okay, I think we did it right. Seems like. Okay, so now let's calculate the delays. Delay is departs from the queue minus first time. Oops, first is 0. This is, it's this minus this. This is 0. This is 4. This is 5. This is 0. 4 minus 3 is 1. 9 minus 5, 4. 6 minus 5, 1. Here we have 3, 0, and 4. Oh, it's 11, sorry. It's 3. I subtracted 12 minus 8. Okay. Thanks for that. So we have average. If you do the calculations, you will find the same, 1.91. All right. Any questions? Okay, so let's see also the last. You're going to see the rest of the questions at home. And let me see. Okay, what else? on. This is here. And let's go to this problem. Problem number 3. The transmission schedule for a given flow as shown in this table lists for each second the number of packets sent in the following second. So it's the beginning of the slot anyway. The flow must stay within the bucket filter. What bucket depth does the flow need for the following token rate? Bucket is initially full. Okay, when first case we second, this is the token arrival rate, and the second 4 tokens per second. Do you remember the token buffer? We have arrivals at time 0, we have 8 packets, 1, 4. I'm not going to read the table, we'll go back. So we need to find, so what we need to do basically here is for these arrivals, we need to go draw a table, create a table that says, okay, at this time, so many packets served, this is the tokens that arrive, those are the packets that are left, so I'm in the bucket. That's what we need to do. So we'll do this table and we'll find what I need. The bucket depth anyway. Make sense? All right, let's do that. Problem number 3. Part A, token rate equals 2. So T, I'm going to put from 0 to 5, 0, 1, 2, 3, 4, and 5. What happens? We have new packets, new token, and packets left. All right? So I'm copying the arrivals I'm copying those from this table here, right? At 0 we have 8. 1 we have 4, 1, 0, 6, 1. That's given. It's also given that the token rate, new tokens in every time slot, it's 2. So this of 2's. You agree? In every time slot, I have 2 tokens that serve my packets. Right? That's why we have the tokens. How many tokens are unused? That I'm going to on the packets I have, and then I'm going to update also the packet left line. So that we have 8 packets, we serve 2, we have tokens left 0. We used both tokens. How many packets are left? We have 6 packets left. Why? Because I used only 2 tokens. Only 2 packets. In this case, do you have tokens left from the previous? No. We have 0 here. There is no extra token. So we serve 2 packets, 0 2 packets. So I have how many left? 2, but I had 6 2 here. Previously, so it's 8. So we need to look at the previous. All right, so over here we have another packet arriving, so 9 in total. We serve 2, 0 left, 2, 7. 7 plus 0, 7 minus 2, we have 5. 5 plus 6, 11, minus 2, 0. And 9 plus 1, 10, minus 2, 8, 0 left. What did we use over here? We use the assumption that the, what is that?
5-minute warning.
Thank you. Assume the bucket is initially full. Means at the beginning there wasn't any token left. So this means that the time minus this was 0. So we cannot add tokens from the previous, right? So we use that. Okay, so now what is the bucket size over here? It as B. B equals what? The bucket needs to hold the packets left, right? So For this, Exactly. So we need the largest number, which is this guy here. So for this particular, if we want to be okay, we need to have a bucket depth of 9. Make sense? Mm-hmm. All right. So make sense? For the second, to do the same thing for a different token size. I'm going to do it in the next bit over here. Token rate is 4. So we repeat the same graph, the same table. New packets. Tokens left and packets left. We have 0, 1, 2, 3, 4. The first line is the same. 4, 1, 0, 6, 1. The rest here, this is 4 because we have 4 tokens. Okay, and now tokens fill these gaps here. First case we serve 4. We have 4 left, and how many tokens left? 0. Over 4 plus 4, 8. We serve 4. We have 0 tokens left. We have 4. You agree? In the next slot, we have 4 plus 1, 5. New tokens, 4. We have 0 left and 1 packet left. Over here, we have 1. We have 3 tokens, which means we have 3 left and 0 packets left, okay? Over here we have 0 plus 6, 4 tokens, 0 tokens left, and 2 packets left. Am I right or not? Sorry. Six, hold on. 4 plus 6, we have 4 tokens, meaning, what did I do here wrong? 3, oh, it's here. Yeah, we have, yeah, guys, I thought, speed up. Okay, we have 3 tokens left from here. 3 tokens left from here. We have 7 tokens, 6 packets, so token left, and 0 packets. Okay, so let's not, 1 packet in the next slot, 1 plus 4, 5 tokens, 4 tokens left, and 0 packets left. Do you agree? Okay. What is now depth?
Out of time. That's it.
Thanks. B equals 4. Okay? Make sense? Alright guys. Thank you.
And this concludes EE 555 discussion on Wednesday, February 19th.